lower bound, we get a minus 36. Minus 3 squared is 9, 9 over 2, plus 9 over 2. Minus 3 cubed is minus 27. Minus 27 over 3 is 9, but you have minus a minus, which is plus 9. And so what do you got? 48 plus 36 is 84 plus 8 minus 9, so that's, and what do we got here? Minus 64 over 3 plus 9 over 2. Starting to really wish I brought my calculator today. So that's 83. Minus 64 over 3. Somebody put me out of my misery here. Plus 9 halves. I mean, I could work it out, but fine. 6 times 83 minus 128 plus 27, all divided by 6, whatever that is. 397 over 6. Woo! So obviously, there you go. That's the area bounded, which is like, what is that? Give me the decimal. I'm just curious. 66.16. 6666. So. And so these two examples, they pretty well show you how we do these problems. Like, you find the area, which is the one you're after, and then you either divide it up using vertical rectangles or horizontal rectangles. And then the method I'm showing you here is, so once you set up the dA, then you integrate dA to get the total A. Now, if you read a calculus book that's real formal, they will set up these problems in terms of an approximation. Like, they'll set up an approximating sum, right? And then they'll take the limit as the number of approximating regions goes to infinity, and then they'll say, oh, that's an integral. I take a different approach. I use here what's called the infinitesimal method. So the infinitesimal method says, find the relation infinitesimally in terms of differential relations, and then you use the integration to sum it up. Okay? So this is the so-called infinitesimal method. But it's really just a mnemonic for that more formal, write out the finite sum, take the limit as n goes to infinity, go, aha, it's a Riemann integral. So I'm trying to spare you of that limit as n goes to infinity, you know, some blah, 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 blah kind of stuff, because it doesn't really, I mean, it's fine, but this is easier, I think, for students to think through. So, and this, if you're an engineer, this is actually how people tend to write things out. Yep. So anyway, we'll do more of these next week, obviously. All right. So, I mean, it takes a while to do one of these examples, and I should show you like a bunch of them. But I think
7.3 is on what missions?
Everything we've covered up to now. So
7 to 9.
7 to 9, is that right? I can't remember. Did we do 6 on?
Will it be 7 to 10?
Everything we cover will be on. You know, we've covered. I think we'll definitely have covered areas bounded by curves by the test. I mean, we've already started today. So yeah, it'll cover U substitutions and.
Will we cover more than this from now?
More than this?
Yeah.
And we'll do more of the same, but it's all kind of. I mean, there are other.
Like other areas.
There are things that happen. Like sometimes you got a shape where you have to. I'll show you. You have something like this can happen. You have something like. this may be the one curve, and the other curve might look like this. And then you may be finding the area bounded between here and here. And then so you'd have like this shape, and you have that shape, and you have that shape. But the thing is, the top and the bottom for this are different than the top and the bottom for that. And so you'd have to, in general, like break it up to an integral for this piece, an integral for that piece, an integral for that piece, because the setup for the dA is different in the different regions. Sometimes that can't be avoided. I avoided it here by just using horizontal. See, if I had done this, I would have had to have dA1 and dA2 over here, and they would have had a different formula. You know, dA2, well, I don't even want to write it down. It's kind of ugly.
So this answer is very like, it's not a real answer, really, because it's an approximation, right?
Oh, this is not approximate. Like that is the exact area bounded by those curves. What I'm saying is there's more than one way to calculate it. But all of those calculations, if done correctly, will lead to the same answer. You know, it's not like a history essay where we can all have different answers and, you know, all be right. Like, you don't get to have your own truth with math. It is what it is. And well, although we do have a professor here who knows something called fuzzy logic, and there they have something like between 0 being true and 1 being, no, 0 being false and 1 being true, you could have something like with truth value 0.5, whatever that means. You'd have to ask Dr. Rogers because he's the one who does these things, but his thesis is in this fuzzy logic, so, which I know nothing about. I'm a true and false kind of guy, or undecidable. There are certain things which are undecidable. It's possible to ask questions in math which don't have an answer, which are neither true nor false. They're just undecidable. But in fact, a rather famous mathematician proved something along these lines, that essentially if your system of mathematics includes arithmetic, it automatically means that there are questions which cannot be decided, that they're neither true nor false. Anyway, I'm not saying it. I try not to talk about this stuff because I don't know the technical terminology correctly, and if I say it wrong, I will invite a certain type of YouTube commenter to have their way with me. So that's it. So have a good weekend, you guys. I think I was saying Mission 8 was due right now, but I gather you guys are not done with it, so